Hi everyone, and welcome back or welcome to my channel. Today we are going to be talking about some particular types of forces. Last time we focused on Newton's 3 laws and talked generally about forces, the definition of forces, and how to calculate forces from values like mass and acceleration. Now, this time we're going to dive into some particular types of forces so we can get more familiar with how to work with them in everyday life and practice problems that will be coming up soon. So these are the 4 types of general forces that we're going to be going over. So the first is the gravitational, and then we have the normal force, friction, and then tension. A lot of them are very related to each other. So we will start off with the gravitational force because I think that one is more understandable and easier to comprehend since we experience it like every single day. Okay, so the gravitational force, we denote it with the sign F and G. The gravitational force is a certain type of pull that is directed toward a second body. So let's say we have one body over here and another body over here. The gravitational force would be a mutual attractive force between both of them. So we speak of the gravitational force on a body. So we usually mean a force that pulls on it directly toward the center of the body. And we focus in this course, or at least in the beginning of it, when the body is the Earth. So let's say we have the Earth with some continents over here. Okay, so this is our Earth. And then let's say we have a person standing on this Earth. There will be a gravitational pull toward the center of the Earth on every single object that exists on the Earth. Okay, now let's suppose that a body of mass m, so this is a body of mass m, is in free fall with the free fall acceleration of magnitude g. We talked about this before. You can go back and watch some of our kinematics videos if you don't remember this, but it's falling with a free fall acceleration of magnitude g. So if we neglect the effects of the air, the only force acting on the body is the gravitational force, F of g. And we can relate this downward force and downward acceleration with Newton's second law that we learned in the last video, which says that F equals ma, or I should be more precise and say F net. So we can place a vertical y-axis, so this is the y-axis, in the vertical direction along the body's path with the positive direction pointing upwards. And for this axis, Newton's second law can be written in the form F net in the y direction equals m times acceleration in the y direction, which in our situation becomes negative F g, the gravitational force, equals m times negative g. Or, in other words, Fg equals mg. So we should take a second here to recognize the importance of signs and reference frames. In this case, we have defined the y direction to be pointing upwards, the positive y direction. So because both the gravitational acceleration and the force of gravity are pointing downwards, we put negative signs in front of both of the values. Okay, so this equation over here tells us that the magnitude of the gravitational force is equal to the product mg, or at least in our case here. We'll talk about more specifics on how to calculate a gravitational force if the object is very far away from the Earth, but that will be coming up in a later lecture, so we don't have to worry about that now. Okay, so the same gravitational force or the same magnitude still acts on the body even when the body is not in free fall but is, say, for example, at rest on a table or moving across a table. So we can write Newton's second law for the gravitational force in these vector forms. So we have the force of gravity, the vector, is equal to the negative force of gravity in the j unit vector. And this equals negative mg times the j unit vector, which equals m times the g vector. Okay, and this tells us that the gravitational force vector is equal to the mass times the free fall acceleration vector directed downwards. Okay, so now closely related to the force of gravity is a value called the weight, or we'll note it as W, of a body. And this is the magnitude of the net force required to prevent the body from falling freely as measured by someone on the ground. So for example, let's say let's say this is someone's hand and it is holding a ball. I apologize for my bad drawing, but let's just say this is someone's hand and there is a ball on the hand. So to keep the ball at rest on the hand while the person is standing on the ground, the person must provide an upward force from the hand to the ball that balances the gravitational force. The gravitational force is here from the earth on the ball. So let us suppose that the magnitude of the gravitational force is 2.0 newtons. This means the weight of the ball is 2.0 newtons. So the weight is 2.0 newtons as well. And we can also say that the ball weighs 2 newtons and speak about the ball weighing 2 newtons when we talk about it. So this means that, for example, a ball with a weight of 3 newtons would require a greater force from this hand, namely a 3 Newton force, to keep it at rest. And the reason is that the gravitational force you must balance has a greater magnitude, and thus we say that the second ball is heavier than the first ball. Now, to generalize the body, we can consider a body that has an acceleration of, acceleration of 0 relative to the ground, which we again assume to be an inertial frame. So this means that two forces will act on the body. We have a gravitational force acting downward, and then we have a balancing upward force of magnitude W, which will be our weight. And now we can use Newton's second law again and say that the F net in the y direction is equal to m times acceleration in the y direction. And in our situation, this becomes weight minus F of g equals the mass times 0, because it's at rest. It has an acceleration of 0. Or this tells us that the weight equals F of g when the object is not accelerating. Okay, so now that we have talked about the gravitational force and the closely related weight, we're going to talk about the normal force. So let's just say that this person is standing on a mattress and the earth pulls the person down, but they remain stationary. And the reason is that the mattress, because it deforms downward, pushes back on the person. And similarly, if we remove the mattress and the person is just standing on the bare hardwood floor, the hardwood floor also deforms even if we don't notice it, and it pushes back up on the person. And the push on the person from the mattress or the floor is known as the normal force, denoted with F and a capital N. Let's place a vector on that. Okay. So the name comes from the mathematical term normal, meaning perpendicular, and this is because the normal force is always perpendicular to the surface. If this is the floor, then the normal force acts at a 90-degree angle from the floor. Okay. So let's say that we have a block standing on a table. Okay, here's our table. And we have the force of gravity on here from the earth pointing downwards. And balancing that force is the normal force from the table, right? So if we want to draw a free body diagram, so here is our object, which is usually represented by a dot by a free body diagram. And let's just define our x-axis and the y-axis. Okay, so we can say that the normal force is pointing upwards along the y-axis, and the gravitational force is pointing down on the y-axis. And notice how the sizes of the arrows are pretty similar. That's because they're equal to each other, because they must balance each other out so that the block doesn't accelerate according to Newton's second law. So we can substitute the values into Newton's second law, and say that the normal force minus the force of gravity equals the mass times the total acceleration in the y direction, and this is just F net in the y direction. So this tells us that the magnitude of the normal force equals the weight, or mg, plus mass times the acceleration in the y direction. We can use the distributive property and get this. For any vertical acceleration, a of y of the table and block. Now, if the table and block are not accelerating relative to the ground, then this tells us that ay equals 0, and we get that the normal force equals mg. So we spent quite a bit of time talking about gravity and normal forces and how they relate to each other. So now we're going to talk about something that's a little bit more complex. We're going to move on to friction. So let's say we want to slide a block, let's say just a box, over a sort of bumpy surface, okay? So if we want to push the block over that way, the motion is often resisted. It's sometimes a little bit hard to push the block because there is a bonding between the body and the surface over here. So the resistance is considered to be a single force, friction. We denote it usually with a lowercase f. And this force is always directed along the surface and opposite the direction of the intended motion. So in this case, the friction would be pointing this way along the surface. And sometimes if we want to simplify a situation in some problems, friction is assumed to be negligible, but that really just depends on the problem that we're dealing with. Okay, so the last and final force we're going to be talking about is tension. So let's say we have a body over here, and we have a rope that someone is pulling. Okay, so there is a force that will be applied on this body, and this body is moving to the right because it's being pulled to the right, and this force is called the tension force. And the tension force, which we denote with T, is always directed away from the body and along the cord or rope that it's pulling. And the tension in the cord is the magnitude T of the force on the body. So let's say if the force on the body from the cord has a magnitude of T equals 50 newtons, then the tension in the cord is also 50 newtons. And usually we assume that the cord is massless and unstretchable, so it only exists as a connection between the two bodies because this simplifies the problem, so we don't have to worry about the properties of the cord, which would make it a lot more complicated. And it's important to note, let's say someone is pulling with their hand on this cord. Okay, there's the hand. And it's important to note that the tension in both directions will pull on both bodies with the same force magnitude T. So this will also experience a force T, like that. If we have like a pulley, and we have a block here, and then we have another block here, if the tension in the cord here is T equals, let's say, 50 newtons again, then there will also be a tension, same tension T here, equal to 50 newtons. And even if the bodies in the cord are accelerating around a massless, frictionless pulley, they will have the same tension. So thus, we can say that the net force on this pulley over here is 2T. Oops, sorry, that should be pointing downwards. It should be 2T, or 100 newtons. Okay, so thank you very much for listening to this lecture on the types of forces. I hope you've learned something new, and stay tuned next time where we will go over applications of Newton's laws and more practice problems.